Hello, hello, and welcome to our demonstration for Robot Lab Live. This is Soft Robot Wormery. I'm Isabel, and this is Simon. And we're part of a team of PhD students at Edinburgh Centre for Robotics, which is a partnership between Heriot-Watt University and the University of Edinburgh. We all work on very different areas of robotics, but we've joined forces to work on this project, which we hope will show you the potential of soft robots. Now, traditional hard robots aren't going to be replaced anytime soon. They do a fantastic job at what they do, but there are lots of environments where they struggle. So we're going to show you an example of this using TurtleBot. This is a low-cost hard robot kit, which is often used in undergraduates' robotics courses. And here we're showing you a situation where those traditional wheels and motors completely fall down. So terrain like sand or gravel or rubble, you can see TurtleBot is just spinning its wheels, digging itself in, and not really able to move. Despite what the name TurtleBot suggests, you definitely could not put that in water. But these are the kinds of situations a robot might face in a search and rescue scenario. Now, more expensive robots with special adaptations could be able to cope with varieties of terrain, but we thought maybe we could take a different approach.
I'm Simon. I'm the lead designer on the project, and I'm going to tell you about what we made. So we wanted to make a robot that could handle itself in disaster situations. So we wanted it to be able to move over loose ground, so gravel, sand, dust, anything that made the TurtleBot wheels spin. We wanted to completely overcome that. Next, we wanted to be able to get through tight spaces. So if there's rubble, we wanted the robot to be able to crawl through those tight spaces and find anything inside. And if a rock fell on the robot, we didn't want it to break. So it had to be made of soft materials. Finally, we wanted the robot to be able to survive water, because most robots are made of electrical components that when they come into contact with water aren't very happy. So we combined soft robotics principles and bio-inspired design to create a robot based on a ragworm. So these creatures are very common to beaches in the UK. They live inside the sediment with all the rocky, sandy areas. They have pincers at the front. They have muscles down the side, and these spikes down the side are called parapodia, which means almost feet. These creatures can move their little legs and burrow into sand, which means they're amazing in tight spaces. So what we did was we decided to copy nature, but you don't want to do it directly because nature's had millions of years to perfect this, and we had a few months. So we decided to translate it into an air-powered system rather than the hydraulic power that these animals use. They pump fluid into their muscles to let them wiggle around. We decided to use air. So we've got these bubbles that I'll show you later that we fill with air. And when we do, the robot can turn either direction. And then we've got these little legs that copy the parapodia on the side of the ragworm that can allow it to move forwards. Then when the air is added through software, we can control everything from the comfort of a chair next to the robot with a laptop, and it'll move in sequences we program. So if we can look at Wayne Mark II on the table here. So it's made from silicone to make sure that if it gets in tight spaces, it can get out again, and that it won't be damaged by anything hitting it. And if I just scrunch it up completely, it'll return to its original position without any damage. The spine is made of dragon skin, a type of silicone that is very flexible, as you saw, but not very stretchy, which means when we take a softer silicone, like this EcoFlex, when we fill it with air, it can push against itself and bend the robot. These parts are made using 3D printed molds. So I 3D printed these with my own printer. So we pour the silicone inside the voids and then take this 3D printed insert, put that in there, squishes the silicone out and makes something with holes. And then we cap those things off with dragon skin so that we can add air to these bubbles and bend things. We make our legs in the same way. So here's an example of a leg that was made using one of these molds. Just pull it off there. See, it's like a sock for your thumb. This is how we made the spine. So we have this thing that's screwed together, and we make the spine, and we cut off whichever bits we don't want. And that's how we make that. So let me just show you quickly how he works. So I have syringes full of air here attached to these hoses you can see on the sides of him. And when I pump air into the bellows, he should turn. So on the left side, his bellows are going to inflate, and he turns to the right. I'll just show you that again so that, I have to do it quickly, otherwise it doesn't work. So do that again. There you go. So he can turn left, he can turn right, he can wiggle, all very useful. And the legs are also made of a difference between a stiffer and a softer material. So the green is softer, what used to be orange but faded, and the blue is harder. So that in the front left leg, you can see that when I put air into it, he'll push himself up and forwards as the leg moves backwards and down. So this just shows you how far the stiff bit at the end of his leg moves, which is very similar to the way ragworms move on sand. So this is Wayne Mark III. This one is much shorter, which was to hopefully make him lighter. And then we reinforced the legs so that it could do more crawling than wiggling. So as you can see, when the front legs inflate with air, they pull him up and forwards. And then when they deflate, they go and push forwards like a ragworm's leg would, moving in a circular pattern like that. So ragworms have 3 movement modes. They have a slow crawl, which is what we're showing here, where they move each of their sets of legs in turn in a cyclical pattern, which means they can crawl along the seabed at constant speed. It's a very robust movement mode, and that's why we wanted to use it. He's moved halfway across the screen now. He's lightning speed. The second movement mode is the fast crawl, which is faster than this, but it takes a bit more programming, and it takes stronger muscles on the sides, and it takes more air. So we chose to use the slow crawl, but basically he would use the muscles on the side to move in an undulatory pattern while putting the legs down at the apex of the wave, which propels the worm forwards a lot faster. And the third movement mode is the swim, where the worm would undulate quickly and use its legs to sort of catch the water and propel itself forwards. So I'm going to hand off to Isabel now, who is going to tell you about what else Wayne can do.
I'm going to tell you about another benefit of using materials and actuators like this, which is that Wayne is very waterproof, can actually be submerged in water, no problem, just like its ragworm counterparts, which is definitely something that TurtleBot cannot do. We designed him for use on land, but thought, given that all of these materials could go in water, why not give it a try? So what we're going to show you now is Wayne swimming. So it swims a bit differently to how Simon described ragworm swimming, but by inflating and deflating chambers, we can change the buoyancy at different parts of the robot. And actually, if we do that in a particular pattern, we can get it to swim forwards. And if we change the pattern, we can actually get it to swim backwards. So if we change the sequence, you can see that we can also get Wayne to swim backwards, which was, a serendipitous discovery. So that's the end of our demonstration for today, but we're happy to answer any questions you have.
If it's pneumatic, does it need a gas source or gas tank, which may limit its mobility?
Yes, so I forgot to mention, we have a silent air compressor just in the back here. So it's got a gas tank that can hold like 8 bar of pressure. We put the system up to 1.2 bar because we have exploded parts of Wayne in the past by putting up the pressure too high. And then we have electronic valves in quite a large cardboard box full of tubes and valves for the air to go through that also has all the electronic components in it. And we put air through that, control the valves in turn, and we have to be really careful because the valves work at a certain frequency, and we've tried to make them work too quickly before and exploded legs of the robot. So yeah, we use a cool pneumatic system that's quite big and cumbersome, but it could be made smaller if we had better resources for this project. Another thing we could do to improve the robot is we could add, say, pressure sensors, and as Claire pointed out in the last demonstration, we could add reinforcement so that he's less likely to have any punctures if he comes into contact with, say, sharp metal from reinforced concrete or something. So maybe we could even make him out of self-healing materials. That would be a really cool thing to try out in the future.
Have you thought about reducing the quantity of tubes?
Yes, so we've thought about reducing the quantity of tubes. They do cause him to sink a bit more than we'd like. The way to do that would be to maybe have tubes with connectors inside coming into the robot from different angles. So where we have 2 tubes, 1 for each leg, we'd have 1 tube that would split off into 2. Turns out connectors for tubes like this are quite expensive. It was about £40 for a connector from a 3mm tube to a 4mm one. We did use a 3D printer to print some connectors, but they don't really like the material difference between the different kinds of tube. So, but yeah, there are definitely ways to do it. Just need more resources than we had during this short project. But good question. Thanks for answering. Thanks for asking.
If one tube is damaged, is the robot still able to function, maybe just at a bit of a reduced level? Yes, we found that many different combinations of leg movements worked for moving forward. So we could also get crawling movements, even if, say, one leg is damaged. But also, I think in potential future work, we would want to have a system that has a lot more legs, like the ragworm, and then you introduce a bit of redundancy into the system. So even if a pair of legs is broken or a section of bellows doesn't work, you can still get the movements that you want to see. Mm-hmm. So that's a great question. Thank you.
Thanks for coming along to Robot Lab Live. You've been a great audience, and everyone who's come before has been amazing as well. Just really glad that we got the opportunity to take part in this. So thanks very much, everyone, and thanks to the Robot Lab Live team for including us.